Our fifth lecture video on work, power, and energy will cover the topic of energy. Energy and work are very closely related. In fact, energy is defined as the ability to do work. There are many different forms of energy. There's mechanical energy, which is associated with the motion and position of an object. One example of mechanical energy could be wind energy, or looking at the energy of the wind turbine blades while they are spinning. Another form is electrical energy, like lightning. Solar energy, which can be harvested from the sun using solar panels. Fluid energy, or the energy acquired in a hydroelectric power plant. Chemical energy, like the energy in a battery. Atomic energy, generated at a nuclear power plant. And sound energy, to name a few. In our class, we are going to focus on mechanical energy, which, like I mentioned before, is associated with the motion and position of an object. There are two main forms of mechanical energy that we will take a look at. Potential energy is first. It is the stored energy of a body due to its internal characteristics. Kinetic energy is the other form of mechanical energy. It is the energy due to the mass and velocity of a moving object. Looking a little bit closer at potential energy, there are actually several different forms of potential energy. There is internal potential energy, which is determined by the nature or condition of the substance. Some examples of internal potential energy might be a compressed spring. There's a lot of energy just waiting to be released if you let go of the spring. A stretched rubber band also has a good deal of internal potential energy. Another example would be gasoline. By itself, gasoline doesn't do much, but if you hold a match to some gasoline, it goes up in flames. Gravitational potential energy is the other form of potential energy. It is determined by the position of an object relative to a reference level. As an example, a rock on the edge of a cliff would have a lot of gravitational potential energy relative to the ground. In this class, we will only be calculating gravitational potential energy. We won't be doing anything else with internal potential energy. From here on out, when I say potential energy, I am talking about gravitational potential energy. If we want to calculate gravitational potential energy, or potential energy, we can use the formula PE equals m times g times h, where PE stands for potential energy, m stands for mass in kilograms or slugs, g stands for the acceleration due to gravity, which is either 9.80 meters per second squared or 32.2 feet per second squared, and h is the height above the reference level in feet or meters. The units for potential energy will be foot-pounds in the English or standard system and joules in the metric or SI system. Let's take a look at an example of potential energy. A roofer with a mass of 68.5 kilograms climbs to a height of 6.00 meters on a ladder. How much work does he do? And what is his increase in potential energy? First, let's write down all of our data to solve for the amount of work done. The roofer's mass is 68.5 kilograms. The height s the roofer climbs is 6.00 meters. Since he's climbing vertically, we will need the acceleration due to gravity g, which is 9.80 meters per second squared. We are trying to find work w. The basic equation for work is the force in the direction of motion times the displacement. In this problem, we have the displacement, which is just the vertical height the roofer climbs to. However, we don't specifically have the force given to us. Instead, the force in the direction of motion will be in the vertical direction, which actually will just be the weight force of the roofer. Since we don't have his weight or weight force, we need to calculate that by taking his mass times the acceleration due to gravity. We can use both of these equations as our working equations, so our next step is substitution. To find the weight force, we will take 68.5 kilograms times 9.80 meters per second squared. This gives us a weight force of 671 newtons. Now that we have the weight or the weight force applied in the direction of motion, we can take the weight force times the height to find the work. 671 newtons times 6.00 meters gives us work of 4,030 newton meters, or 4,030 joules. In the second part of the question, we are solving for the roofer's increase in potential energy. Our data can say written in the same way. The only difference is now we are trying to find the potential energy PE. The basic equation for potential energy is that the potential energy is equal to the mass times the acceleration due to gravity times height. Our basic equation will also be our working equation because it is written in terms of PE. Our next step will be to substitute our data. PE equals 68.5 kilograms times 9.80 meters per second squared times 6.00 meters. Multiplying, this gives us PE of 4,030 kilogram meters squared per second squared, which is the same thing as 4,030 joules. You can see that the work the roofer does is the same as his increase in potential energy, which makes sense because energy technically is the ability to do work, so work and energy are closely related. This concludes our discussion on energy basics and potential energy.